In this video I will solve total 6 exercise problem regarding clipper circuit, and I will suggest you to follow all the 6 problems so that you get a total idea about clipper circuit. And I will try to cover all kinds of circuit configuration related to clipper circuit. That's why I will suggest you to follow this whole video, and don't forget to subscribe my channel for upcoming videos. So this is the first problem. In this problem I have to sketch the output waveform for this network, and I have to consider the diode is of silicon. See, this is here we have a resistor R of 500 ohm and the load resistor equal to 10 kilo ohm. We have a diode D here, and we are applying a sinusoidal voltage here in the input side with positive peak of 20 volt and negative peak of minus 20 volt, and we have to consider this diode is made of silicon. When in any clipper circuit we are told that the diode is made of silicon, that means we have to consider the barrier potential of the diode as equal to 0.7 volt. Okay, now let me analyze this circuit. When analyzing a clipper circuit, we have to look up for two different conditions. At first we will see, is there any bias voltage, additional bias voltage in this circuit or not. If there is no additional bias voltage, then I will apply just only simple forward and reverse bias formula in case of this diode. But if there is an additional bias voltage in the circuit, at first we have to identify the transition voltage which will separate the region for the diode is to be forward biased and is to be reverse bias. So as there is no bias voltage here, I will just use the simple forward and reverse bias of this diode. So during the positive half cycle of the input voltage, this terminal will be positive and this terminal will be negative. See, the positive terminal will be connected with the inside of the diode, and the negative terminal will be connected to the P side of the diode. That means the input voltage, when it is in positive half cycle, will try to drive this diode in reverse bias. So when a diode is in reverse bias, I can replace that diode with an open circuit. So now let me do that. As the diode is replaced by open circuit due to its reverse bias, our new circuit will look like this during the positive half cycle, and you will see that the input voltage with maximum value of 20 volt is dropped across this R and the load resistor RL. That means the during this positive half cycle our output voltage will follow the input voltage, but there is a slight problem with the peak value of the output voltage, because the input voltage is dropped across this 500 ohm and this 10 kilo ohm. Therefore when the input voltage Vi is equal to 20 volt, that means when the input voltage is at its maximum value, then our output voltage will be equal to VO equal to, we can find that by using the voltage divider rule in this circuit. 10 kilo ohm divided by 10 kilo, this is 500 ohm, which is equal to 0.5 kilo into the maximum value of the input voltage 20 volt, which will give us a value of 19.05 volt. That means from during the positive half cycle our output voltage will be equal to, so this is 0, this is pi, and this is twice pi interval. From 0 to pi our output voltage will follow the waveform of the input voltage, but it will have a peak value of 19.05 volt. Okay, now consider the negative half cycle of the input voltage. That means the voltage from pi to twice pi interval. In that case this terminal will be negative and this terminal will be positive. See, the positive terminal is connected with the P side of the diode and the negative terminal is connected with the inside of the diode. That means as the P side of the diode is connected with the positive terminal and inside is connected with the negative terminal of the source, I can conclude that input voltage will now drive this diode in forward bias. So when this diode is in forward bias, as we are specifically told that this diode is made of silicon, I will replace it with a voltage source of 0.7 volt, and there is a conventional way of replacing this silicon diode with its barrier potential. If this is a diode, it is its p side and this is its n side. So if I replace this diode with its built-in potential, the positive terminal of the 0.7 volt will be in the p side and the negative terminal of the 0.7 volt will be in the n side of the diode. So during the negative half cycle of the input voltage, our diode will be in forward bias. So I will replace the diode with its barrier potential or junction voltage. Therefore our new circuit will look like this, and you will see that as long as the input is going through negative half cycle, our diode will be in forward bias. That means during this total half cycle I can replace that diode with this voltage source. So you will see that I am taking the output across this terminal and this terminal, which is connected in parallel with this 0.7 volt voltage source, and the source has its negative terminal in upward direction and the positive terminal in downward direction. So output will be equal to minus 0.7 volt for this total negative half cycle, which I can show like this, whose value is equal to minus 0.7 volt. Now I will run a simulation to verify my circuit analysis. See, this is the circuit arrangement I have set it up in the multisim simulator, and now let me run the simulation. See, here I am showing the output in red waveform and input waveform in blue color. So if I show you the waveform, you will see an waveform like this. The red waveform is our output waveform and the blue waveform is our input waveform. See, when I am showing the input in channel 1 and showing the output in channel, I am showing the input at channel A and output in channel B. Now look at the output. When the input is nearly equal to 20 volt, 19.906, that means 19.91 volt, our output is equal to 19.094 volt. See, here I have deduced that when the input voltage is at its maximum value, our output is equal to 19.05 volt. That means this implies that my analysis is quite accurate, and during the negative half cycle of the input voltage, you'll see that our output voltage is equal to minus 725.734 volt during this entire negative half cycle. Okay, see, the red line is constant during the entire negative half cycle, and this minus 725.734 millivolt is nearly equal to minus 0.7 volt. After that I will show you my second problem. So this is my second exercise problem regarding clipper circuit. So this is our circuit, and for the circuit we have to sketch the output waveform for this circuit with the given waveform. That means I am applying a square waveform with positive peak plus 20 volt and negative peak minus 20 volt, and we have to consider this diode. This diode is made of silicon. That means when this diode is in forward bias, I will replace this diode with a voltage source of 0.7 volt, and the convention of replacing the diode with its voltage source is this. Let's say this is our diode when it is in forward bias. That means positive terminal of the source is connected with the p side and the negative terminal is connected with the n side. Then I will replace this with its equivalent voltage built-in potential, and the positive side of the voltage source will be in the p side of the diode, and the negative side of the source will be in the n side of the diode, and the value of this voltage source will be 0.7 volt. See, here we have an additional bias voltage of 3 volt. When we have an additional bias voltage of 3 volt, that means at first our task is to identify the transition voltage which will separate the region for this diode to be forward biased and the region the diode will be in reverse bias. So to do that we have to proceed this way. During the positive half cycle, this terminal will be positive and this terminal will be negative. That means the positive terminal of this input voltage is connected with the p side of the diode and the negative terminal is connected with the n side of the diode. That means this input voltage during its positive half cycle is trying to drive this diode in forward bias. Now consider this bias voltage. Its positive is also connected in P side and negative is connected with the inside of the diode. That means during the positive half cycle of this input voltage, both these input voltage and this bias voltage is trying to drive this diode in forward bias. So in this region of the input voltage, the diode will be in forward bias or in on state. Now consider the negative half cycle of this input voltage. During the negative half cycle, this terminal will be negative and this terminal will be positive. If I consider the biasing of this input voltage, I will see that the positive terminal is connected with the N side and the negative terminal is connected with the P side of the diode. That means this input voltage is trying to drive this diode in reverse bias. That means this input voltage is trying to drive this diode in reverse bias. Now consider the biasing condition of this 3 volt. You will see that the positive terminal is trying to drive this diode in forward bias because positive is connected with the P side and the negative terminal of the source is connected with the N side of the diode. So there must be a value of the input voltage for which the effect of this voltage Vi and the voltage of this 3 volt will have a neutral effect, or the current through this diode will be equal to 0. And when this input voltage is exactly equal to minus 3 volt, you will see that this input voltage will totally minimize the effect of this 3 volt. That means 3 volt minus input voltage equal to minus 3 volt will be our transition voltage. So when input voltage is equal to minus 3 volt, for any value above this input voltage, our diode will be in forward bias, and for any value below this voltage source, our diode will be in reverse bias. Now consider the two region. When the input voltage Vi is greater than our transition voltage, this is our transition voltage is minus 3. When the input voltage is greater than minus 3 volt, when the input voltage is greater than our transition voltage, this diode will be in forward bias. So when this diode is in forward bias, I can replace this diode with its built-in potential. So when our input voltage is greater than transition voltage, our input voltage Vi will be equal to 20 volt, and you will see that this terminal is negative and this terminal is positive. Okay, now if I apply Kirchhoff's voltage law in this loop, I will get our desired output voltage. See, we are taking the output across this load resistor, so this terminal is its positive and this terminal is its negative. And if I apply Kirchhoff's voltage law, at first I will encounter this input voltage of 20 volt and its negative polarity, so its voltage will be positive plus 20. After that I will encounter this 3 volt and its negative polarity, so its voltage will also be positive plus 3. After that I will encounter this 0.7 and its positive polarity, therefore its voltage will be negative. And after that I will see this load resistor and its positive polarity, so its voltage will also be negative, VO equal to 0, from which I can calculate our output voltage VO equal to 22.3 volt. Okay, so during the positive half cycle, our output voltage will be 22.3 volt. Now consider the value of input voltage Vi, which will be less than the transition voltage TV. In that case, this diode will be in reverse bias. So when this diode is in reverse bias, I can replace this diode with an open circuit. Now let me do that. Due to reverse bias of the diode, I have replaced the diode with an open circuit. When the diode is replaced with an open circuit, the current in this circuit will be I equal to 0, because there is no current flow in an open circuit, and we are taking the output across this load resistor of 10 kilo ohm. So our output voltage will be equal to 10 kilo ohm into the value of this current, and the current is equal to 0. Just simple application of Ohm's law. 10 kilo ohm into 0 equal to 0 volt. That means if I draw the output waveform, you will see an waveform like this. During positive half cycle, you will get an output voltage of 22.3 volt, and during the negative half cycle, an output voltage of equal to 0 volt. Okay, so this will be our output waveform given VO equal to 22.3 volt, and this is equal to 0 volt within the negative half cycle. Now let me run the simulation. I am applying square waveform with frequency 50 Hz and amplitude, positive amplitude 20 volt and negative amplitude minus 20 volt with 0 offset. And this is our problem circuit I have set up in this simulator. This is the output voltage. Now see, I am showing the output in channel B, and I am taking the input from channel 1 with a red waveform, and I am taking the output with a green waveform. And you will see that, look at the positive half cycle. During a positive half cycle of the input waveform, our channel A is showing a value of 20 volt, and the output is equal to 22.423 volt, which is nearly equal to our 22.3 volt. And during the negative half cycle of the input voltage, you will see that input voltage is equal to minus 20 volt, and output is equal to minus 320.033 microvolt. Now, from where did the voltage come from? See, when a diode is in reverse bias, the diode is not entirely open circuit, rather a small amount of leakage current is always in flow through the diode. Therefore, as there will be the current will not be exactly 0, but it will have a value of 10 to the power a scale of 10 to the power minus 9 ampere. So if I multiply this 10 to the power 9 minus 9 ampere with this load resistor, I will get a value of output voltage in the scale of microvolt, which is showing in my simulation output. Okay.